Hey everybody, we're going to talk about 2.2 function notation. All right, so we're just going to talk about this example because you may have seen function notation before. But Rachel's parents keep track of her height as she gets older. They plot these values on a graph and connect the points with a smooth curve. For every age you choose on the x-axis, there is only one height that pairs with it on the y-axis. That is, Rachel is only one height at any specific time in her life. In math, a relation is any relationship between two variables, and it doesn't have to be anything, really. As long as you have two variables, it's a relation. A function is a special type of relationship between two variables such that for every value of the independent variable, there is at most one value of the dependent variable, right? So sometimes we say each input only has one output. A function is a special type of relation. If x is your independent variable, a function pairs at most with one y with each x. You can say that Rachel's height is a function of her age. You may remember the vertical line test from previous mathematics classes. It helps you determine whether or not a graph represents a function. If no vertical lines cross the graph more than once, then the relation is a function. Take a minute to think about how you could apply this technique to the graph of Rachel's height and the graphs of the next example. So if we look at like when she was 4, you go up and we say she was only one height when she was 4. When she was 5.5, she was only one height. All right, hopefully that kind of makes sense. And then the two graphs up here, we have a function. That the one over here is a function, right? Because each input only has one output. The vertical line only crosses the graph one time. And then if we rotate that graph to the side, now we have this thing is not a function. We have a vertical line right here, and it goes up and down, and it crosses our graph at 2 points. Okay, so as long as the vertical line passes 2 points at any spot, it's going to not be a function. So you don't have to have like a whole graph of something like this. You could even have one that's like this, and then if I have a single point, this is no longer a function, right? Because if I do the vertical line test right here, it passes through this point and that point. All right, so function notation emphasizes the dependent relationship between the variables that are used in a function. The notation y equals f of x indicates the values of the dependent variable y are explicitly defined in terms of the independent variable x by the function f. You read y equals f of x as y equals f of x, right? When I say it, it's kind of the same thing. But f is not a variable. Okay, graphs of functions and relations can be continuous, such as the graphs of Rachel's height, or they can be made up of discrete points, such as the graph of a maximum temperatures for each day of the month. Although real-world data often have identifiable patterns, a function does not necessarily need to have a rule that connects the two variables. Okay, so here's an example. Function f is defined by the equation right here, and function g is defined by the graph. Okay, find the value. So f of 8, we're going to place x with 8. So every x that you see, so I have 2 times 8 plus 5 all over 8 minus 3. 2 times 8 is 16 plus 5 all over 8 minus 3 is 5. So I get 21 over 5, which is 4.2. All right, so that means f of 8, so we could write it as f of 8 equals 4.2. Okay, if I want to try f of negative 7, I'm going to plug in negative 7. So I'd say, I'm going to do this in a different color. I have 2 times negative 7 plus 5 all over negative 7 minus 3. 2 times negative 7 is negative 14 plus 5 all over negative 10 this time. And we get negative 9 over negative 10. The negative should cancel out, and we'll get f of negative 7 equals 0.9 or 9/10. You can write it as a decimal or a fraction. I don't really care. Okay, next, g of 1. What I need to do is plug in 1 for the x, so I go to the x-axis. Here is my 1, and I go up until I hit the graph, and that is at 3. So g of 1 is 3. G of negative 2, I have to plug in negative 2 for x, so find negative 2 on the x, which is right here. Where does it cross the graph? It's right at 0. So